Imagine a robot deployed in the aftermath of a wildfire, navigating through collapsed buildings, searching for survivors. It doesn't know where the victims are, only that they're somewhere in a vast, unstructured environment. Every action it takes, where to move, what to scan, must be chosen carefully. Too much exploration and it wastes time and energy, too much exploitation and it might miss the target entirely. This is active search, a fundamental challenge in robotics, where autonomous agents must adaptively decide what to observe and where to go, balancing the trade-off between exploring unknown areas and exploiting prior observations. Traditional approaches to this problem have relied on greedy, myopic strategies, like choosing the next best sensing location based only on immediate information gain. While simple and fast, these methods are suboptimal. They fail to consider long-term consequences, especially in noisy, partially observable environments. In contrast, look-ahead planning, where agents simulate future sequences of actions, can dramatically improve performance. But this comes at a steep cost, building and simulating massive search trees, which becomes computationally intractable as the environment grows. Now here's the breakthrough. In this work we propose Cost-Aware Diffusion Active Search, CDAS, a novel framework that uses diffusion models not just as generative tools, but as planners. Instead of exhaustively building a search tree, we train a diffusion model to sample high-quality action sequences over a finite horizon, sequences that balance exploration and exploitation, while respecting real-world costs like travel distance and sensing time. But it's not as simple as applying existing diffusion models to decision-making. We discovered a critical flaw, optimism bias. When trained on data from a myopic, greedy agent, diffusion models tend to overestimate their future success. They generate deterministic, overly optimistic plans, like assuming the target will be found on the very first scan. This leads to poor coverage and failure to explore effectively. To fix this, we introduce a gradient-guided approach. We train two models, a trajectory generator that produces action sequences and a return estimator that predicts the expected cumulative reward, full recovery of all targets, over the horizon. During inference, we use the gradient of this return estimate to steer the diffusion process toward more balanced, realistic plans. We also incorporate a distance estimator, a neural network trained to predict travel cost, so the agent can make cost-aware decisions without relying on ground truth simulations. The result? A system that outperforms standard baselines in both full recovery rate and computational efficiency. In one-dimensional environments, CDAS recovers targets in the minimum number of measurements, outperforming even shallow tree search methods like CAST. In two-dimensional grids, it matches or exceeds the performance of Thompson sampling and offline reinforcement learning algorithms, all while being significantly faster per decision step. And here's the real advantage: amortization. Tree search algorithms like CAST must resimulate thousands of trajectories at every decision step. In contrast, CDAS samples dozens of look-ahead sequences in a fraction of the time, thanks to the learned generative model. In our experiments, we saw over 30% faster decision-making compared to CAST, even in larger environments. This efficiency scales beautifully. In a complex 8x8 grid with 3 agents and 4 targets, CDAS still outperforms CAST in terms of recovery speed, especially when sensing is expensive. And while CAST still wins in low-cost scenarios due to its exact cost computation, CDAS shows remarkable robustness in high-noise settings, where the ability to generalize from suboptimal training data gives it a clear edge. But why does this work so well? Because we're not just generating sequences, we're learning the structure of the problem. By leveraging inductive biases, like permutation invariance and spatial equivariance, we design neural architectures that respect the symmetries of the search space. Whether it's a UNet for grid-based representations or a graph attention network to model spatial relationships, the model learns to reason about the environment in a way that mirrors human intuition. And crucially, we don't need perfect data. The training dataset comes from a greedy agent that doesn't plan ahead. Yet our model learns to look ahead, generating sequences that are better than the data it was trained on. This is a game changer for real-world robotics, where collecting high-quality, long-horizon trajectories is expensive or impossible. In short, CDAS represents a new paradigm, learning-based look-ahead planning. It combines the expressiveness of diffusion models with the rigor of reinforcement learning, while avoiding the scalability limits of tree search. It's faster, more flexible, and more robust, especially in noisy, real-world scenarios. So what's next? We're exploring multi-agent coordination, integrating communication into the diffusion framework, and pushing the boundaries of how far we can go with generative models in decision-making. But one thing is clear: the future of autonomous search isn't just about reacting to the world, it's about imagining the best possible future and acting accordingly. This is not just another algorithm. It's a shift in how we think about planning, where the agent doesn't just choose the next move, but generates the entire story of its future, one plausible, cost-aware, information-rich sequence at a time. And that's how we're building smarter, faster, more adaptive robots for the real world.